Hello everyone, welcome back to Math with Allison. Today we're working in our sequences and series, so we're going to be talking about what a summation is. So it's going to be very general, so let's go ahead and dive into it. So when we want to think about a series, let's think about adding a long list of numbers. So here we have the numbers 1, 2, 3, 4, so on and so forth, and what we're doing is we're adding them up. So there's a way we can rewrite this so we're not writing like tons of numbers like this. And the first thing that we have is the summation. So this is the summation side. It's that weird Greek letter E, and it means that we're adding up. So second, we have our index. So in this case, K is our index. You can use any letter, like N is very often used, I is used, you can use any letter, but typically these are the most common ones. And we have to have a starting value. So in this case, we're going to be starting at 1. Now, we also have to have an ending number, right? And in our case, we're starting at 1 and we're ending at 13. Okay, and then finally, we have to have what we're summing up. And so in our case, we're summing up K starting from 1 to 13. We're replacing that K with our index each time. So let's talk about what this looks like. When K equals 1, we literally replace K. So we replace K with 1. And then the summation means we're adding, and then we're going to K equals 2. We replace that with our K, so K is equal to 2. We add on, we go on to K equals 3, so we're going to replace that with 3. Adding on K is equal to 4, we get 4, plus, and then going all the way down, we're going all the way until K is equal to 13, where we're adding 13. So another way we could write this is 1 plus 2 all the way down to 13 is equal to the summation from K starting at 1 going up to 13 of K. So when we have an ending value, so we have an ending value of 13, that is called a finite sum. So when we have an actual finite number that we end at, it's called a finite sum, right? We can also have an infinite sum, and it's when we don't have a finite number we're ending at, the addition's going on forever and forever. So let's go ahead and think about a sequence, right? So a sequence is going to be structured like a list of numbers, right? So we have AK, where K is starting at 1 going all the way to infinity. Well, summations often use sequences and add them up. So let's say we're wanting to find a partial sum. So we're not wanting to go all the way to infinity, but we want to have an actual stopping number. So we have s to the n is equal to the finite sum of a to the k, adding all of those sequent terms together. So s sub 1, if we would write it out officially, we would have the summation k going from 1, and then our ending number is going to be 1 of our a sub k. So that seems a little silly. You don't need to write that out. All you need to write out is that this is going to be the first term. If you wanted to write out s sub 2, so that's going to be the partial sum from k going to 1 to 2 of our a sub k terms, you can also just write that as A1 plus A2. So similarly, if you wrote it out officially, I'll just do it one more time. K equal 1 to 3 of A sub k. We're going to have K is equal to 1, K is equal to 2, K is equal to 3, right? So what we're doing each time is we're replacing the K with the actual value that it's equal to. So here, when we have the partial sum going to n, we would have A sub 1 plus A sub 2 plus all the way down until we have A sub n. Now, if we take the limit as n goes to infinity, what we're going to be working with is now an infinite summation. So this would be going to infinity of a sub k. So that's a sub 1, a sub 2, plus a sub 3, going on forever. So here there's no ending value. We're just adding on forever. So now let's go and find some actual examples so we can see how this works. So here we have a sequence, and now I switched it over to n. You can use whatever index you want, right? That could also be a k. So that's equal to 2n plus 3. First, we're going to go ahead and find s sub 1. So the first way you could do it is we have the summation from k equals 1, and now we're only going to 1. It's just going to be the first term, right? And what you could do first is you could have our a sub k's. So it's going to be equal to a sub 1, and here you could plug in what that's equal to. So 2 times 1 plus 3, which is equal to 5. Another way you could do it is in your summation, you could replace it with what it's equal to. So this is going to be 2k plus 3. So here, first we plug in k is equal to 1, so we get 2 times 1 plus 3. And now we have to plug in k is equal to 2 and add those together. So 2 times 2 plus 3. This is going to be equal to, that's going to be 5 plus 7, which is going to be equal to 12. And so that's our partial sum at n equals 2. The third way you can do this is you can actually write out what the sequence is equal to. So we have 5, 7, 9, 11, 13, so on and so forth. So s sub 3 is going to be equal to a1 plus a2 plus a3. That's going to be 5 plus 7 plus 9, which is equal to 12 plus 9, which we know is equal to 21. And so that's how we would find those three partial sums. Here, for problem 2, we're going to write out the summation notation of these 3 sequences. So let's go ahead and do the first one. We have 1/2 plus 1/4, 1/8, 1/16 plus 1/32, and then adding on forever. So what we want to do is write a formula first, right? I want to write a formula for all of these terms. So the terms we have is 1/2, and it goes on forever. Think of this as the sequence portion. It's like we're writing an explicit formula for a sequence. So this, if I was trying to find a formula, I would rewrite it as 2 to the power of, whatever down here in the denominator. So that's 2 to the power of 4, 1 over 2 to the power of 5. And so I know my explicit formula is going to be 1 over 2 to the power of n, or whatever notation you like, 2 to the power of k. So if I want to write this out as a summation, we have k starting at 1 because that's our first exponent, going all the way to infinity because we go on forever, and then you fill it in with your explicit formula, so 1 over 2 to the k. If you write like it with n's, you could do n equals 1 to infinity of 1 over 2 to the k. You could even change your starting index, so maybe we want to start at 0, n equals 0 to infinity. Then what we would need to do is we need to add 1 to the exponent. Since we took away 1 from the index, we need to add 1 to the explicit formula. So remember, there's multiple ways you can write these. I think that's why people start getting so tripped up in Calc 2 is because now there's not one concrete answer. There's not, oh, I start here, I go here, here's the answer, it's black and white. Now there's a little bit of gray area because there are multiple correct answers. So just keep that in mind while you're going through this. Now let's go ahead and try part B. So we have 3 minus 6 plus 12 minus 24 plus 48, so on. Let's think about an explicit formula first. So I notice what's happening each time is that it's being multiplied by a -2. So first we have 3 multiplied by -2 is -6, times -2 is positive 12. So here I'm going to have 3 times -2 to the power of n, right? We're just multiplying by that each time. So now that I have that, or you could have 3 to the -2 to the power of k. So let's write it out with summation notation. We need to think about our starting index. N or k is going to be starting at some number, and I know I'm going to infinity because there's no end, right? So I'm going to have 3 times -2 to the power of n. We want to make sure that we hit the first term. So if I started at 1, I would have 3 times -2 to the power of 1, which is equal to -6, which is the second term. So what I need to start at is 0. So here I would get 3 times -2 to the power of 0 plus 3 times -2 to the power of 1 plus 3 times -2 to the power of 2, 3 times -2 to the power of 4, so on and so forth. I skipped 3. Haha. So this would be equal to, and this is always a really great way to check your work, is to actually write it out. That's going to be 3, right, minus 6. That's going to be plus 12 minus 24, and then so on and so forth. And so now we know that our summation is going to be correct. We got one more, 2 plus 5 plus 8 plus 11, so on and so forth. So let's think about our actual numbers to try to find an explicit formula. So this is not the first thing I noticed. After doing some work, I realized that these are all 1 less than a multiple of 3. So 3, 6, 9, 12, they're all 1 less than that. But I will show you the way I got there. So I'm going to go ahead and show you the long way. So first I added 3. The first thing I thought was maybe it's like adding itself. So 2 is 1 plus 1. 5 is 2 plus 2 plus 1. 8 is 3 plus 3 plus 2. 11 is 4 plus 4 plus 3, right? And if I added the next number, the next one would be 14. So 14 is 5 plus 5 plus 4. Because I was trying to get it in terms of like k equal 1, it's counting numbers. So I was like, if the first one starts at 1, I want to have 1s in there. If the second one starts at 2, I want to have 2s in there. 3s, 4s, so on and so forth. And what I realized was we had this kind of pattern. It's k plus k minus 1, right? And when you add that together, we get 3k minus 1, which then I was like, oh, they're all 1 less multiples of 3. So however way you do it, it's going to be, the best way for you. So here, if I made this, I have the value, I have my little formula, 3k minus 1. K is going to go ahead and start not at 0, but actually at 1, right? Because we want to get that value of 2 going all the way to infinity. So that would be our solution. Okay, number 3, we're going to find the first 4 terms of the sequence of partial sums for the series, and that's going to be k equal 1 to infinity, -1 to the k times k. So let's go ahead and do this. We're going to go ahead and find S1. So S1 is going to be -1 to the power of 1 times 1, which this is going to be equal to -1. So now for S2, what you could do, and every time you can write out the summation notation, but you don't have to, is where you take the previous partial sum and you add on the next term. So -1 squared times 2. That's going to be equal to -1 plus 2, which is equal to +1, right? Now S3 is going to be equal to S2 plus the next term, -1 cubed times 3. That's going to be equal to 1 minus 3, which is equal to -2. And then finally, we have the partial sum at 4 is going to be S3 plus the next term, so -1 to the 4th times 4. Here we get -2, and that's going to be plus 4, which is equal to 2. And those are the first 4 terms. So that's all I have for us today. If you enjoyed this video, I have many more like it, so make sure to check out my playlists. They're linked down below. Otherwise, please give this video a thumbs up and comment other problems or topics you'd like to see done. Thanks for watching.